presenter Gaurish. Today we are going to learn about the hydrogen, which is an important or a simple chapter also from our NCRT, and questions are asked from that in JE. So let's take a glance at what we are going to learn this lecture. We are going to learn occurrence of hydrogen, position of hydrogen in the periodic table, and isotopes, allotropes, and molecular forms of hydrogen, dihydrogen or hydrogen gas, and different atomic forms of hydrogen, water, heavy water, deuterium dioxide, deuterium oxide, and hydrogen peroxide, hydrates. And so let's get into the topics. So position of hydrogen in the periodic table. Before moving to that, we need to just talk about the hydrogen in a little detail. And hydrogen is the most abundant element in the universe, means 70% of universe total mass. However, it does not occur in the Earth's atmosphere in its free form because of the absence of enough gravitational pull to hold the lighter hydrogen molecules, but forms 90% of Sun's atmosphere. The giant planets Jupiter and Saturn consist mostly of hydrogen, and hydrogen is the lightest element and is the first member of periodic table. It was first isolated by an English chemist and physicist, Henry Cavendish, but the name hydrogen was given by Lavoisier due to its water producing nature. So that was about the hydrogen. And now let's have a look at the what is the position, where is the position of the hydrogen in the periodic table. Okay, hydrogen consists of one proton in its nucleus with one planetary electron present in the s orbital of K shell or first orbital. Neutron is absent in its nucleus, and thus its electronic configuration is 1s1 1s1. This configuration is responsible for dual nature of hydrogen, that is behavior like an electropositive element or alkali metals, and as an electronegative elements or halogens. Due to its resemblance with alkali metals as well as halogens, its position is uncertain in periodic table, and we can see the resemblance with both the alkali metals and halogens. First, we are going to talk about the resemblance of the hydrogen with the alkali metals, resemblance with alkali metals. What are the resemblance with alkali metals? Hydrogen shows the following resemblance. I can show that we know that the all including hydrogen have the similar outermost electronic configuration, that is ns1 ns1. Let me show you hydrogen, that is 1s1. Hydrogen is 1s1, while lithium we can see that its configuration is 1s2 2s1 1s2 2s1. And for sodium it is 1s2 1s2 2s2 2p6 2p6 3s2 3s2 3p6 4s1 4s1. And for potassium, these are first group elements, okay? And potassium 1s2 1s2 2s2 2s2 2p6 2p6 3s2 and 3p6 4s1. For sorry, I have done something wrong here, because Sodium, for sodium there are only 11, the atomic number is 11, so there is it is wrong. It will be 3s1, 3s1 here it is 4s1. And for the rest of numbers, it's rubidium 1s2, 2s2, 2s2, 2p6, 2p6, 3s2, 3p6, 3d10, 3d10, and 4s2, 4s2, 4p6, and finally it is 5s1. And for cesium, we can say that it is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10, 4s2, 4p6, 4p6, and 5s2, then 5p6, and 6x1. All of them, we can see that the outer configuration is like ns1. The outer electronic configuration is ns1, so it has such a similarity with the alkali metals. And the second similarity is that all of them are strongly electropositive. Okay, and that is have tendency to lose solitary electron of their outermost shell and to change into the unipositive ions. Both the hydrogen and those alkali metals have that property of the electropositive, strong they are strong electropositive. Okay, and the third similarity is that their normal valency of all of them is 1. They both hydrogen have the valency 1, and also alkali metals have the same valency, that is 1. And all form stable oxides like H2O. H2O is an oxide. Like that, alkali metals form oxides like Na2O, Na2O, K2O, and so many like that. And also peroxides. Hydrogen also form peroxide, that is H2O2, we know, hydrogen peroxide. And like that, others like alkali metals like sodium form Na2O2, Na2O2, and there are so many other examples also. And we know that they are good reducing agents due to their high electropositive character. Hydrogen and alkali metals are similar in those ways. They are also good reducing agents. So these were the similarities with the alkali metals, and now we are going to discuss the similarity of the hydrogen with halogens. This is resemblance with halogens. Okay, with halogens. And the first one it is hydrogen, like halogens, have the tendency to gain an electron, thus change to H minus. They will gain electron and changes to the configuration H minus ion, that is called hydride ion, hydride ion, hydride ion, hydride ion, and acquire the stable configuration, that is 1s2, stable configuration, that is 1s2. And the second property, it is that ionization energy of hydrogen is 313 kilocalorie, 313 kilocalorie. Halogens also show the ionization energy of the same order, that is fluorine shows something like 402 kilocalorie. This ionization energy we are telling about. What is ionization energy? It is the energy required to remove the outermost electron from an atom. Okay, and so like the chlorine have 300 kilocalorie, 300 kilocalorie, and bromine have something like 273 kilocalorie. Iodine also have such a ionization energy, that is 241. All of them have, including hydrogen, have almost same or nearby ionization energy. And the third one we need to know is that in its molecular state, hydrogen is a gas. H2 is a gas. In its molecular state, hydrogen is a gas. Similarly, among halogens, F2 and Cl2, are also gases. Br2 is a volatile. Br2 is a volatile liquid, and I2 is a volatile solid. They are all volatile. I2 is also volatile solid. And the fourth similarity, all of them have diatomic configuration in this molecular state. That is F2, H2, F2, Cl2, and Br2, I2. They all have the diatomic configurations like that of the hydrogen. And next, hydrogen in organic compounds can be replaced by halogens. Okay, we know that the halogenation reactions or some type of that particular reactions where the hydrogen of a organic compound can be replaced by the halogens. So that is because of the similarity of the hydrogen with the halogens or vice versa. And when we talk about the similarities, we need to we also need to talk about the dissimilarities of that hydrogen with the halogens. So what are the dissimilarities of them? The first one it is hydrogen dissimilar. We are talking about dissimilarities. Okay, dissimilarities of halogen, dissimilarities with halogens. What are the dissimilarities? Yes, first one we need to note. Sorry, we need to know hydrogen has much smaller tendency to form H minus ion. We told that hydrogen has the tendency to form H minus or hydride ions, but it is really it have smaller tendency to form such a hydride ion compared to the halogens. And the second dissimilarity, it is that electron affinity of hydrogen, that is 70, almost equal to 17.3 kilocalorie per mole. Kilocalorie per mole. This is the what is electron affinity? It is the tendency of an electron of an atom to attract or gain the electron. That is almost equal to 17.3. That energy is almost equal to 17.3 kilocalorie per mole, and is much smaller than that of the halogens. Halogens have uh, more than 70, not 17, that is 70, more than 70 kilocalorie per mole. Okay, it is therefore suggested that hydrogen be allotted a separate position and not grouped with either alkali metals or halogens. And Thomson assigned a separate independent position to hydrogen on top of the periodic table, like that of this, drawing the model of Thomson. Thomson, I use a different color. Okay, like lithium here, sodium, beryllium, magnesium, boron, aluminum, calcium, silicon, nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine, and the noble gases are of course there: helium, neon, argon. And he placed the hydrogen at the middle of them. Middle of them will be 1, 2, 3, 4, 5, 6. So this will be the middle, and he placed the hydrogen here. That is the middle of this one. Okay, this does not disturb the symmetry of the table, and therefore is no violation of periodic table. In some respects, the hydrogen also resembles carbon of the group 4. He resembles the carbon also, since both have half-filled configuration, half-filled shell of the electrons. Okay, and that means H1. H1 has this hydrogen. Hydrogen has half of the first shell maximum capacity of 2 electrons. Okay, and while the carbon has that of the hydrogen has, oh sorry, carbon has 2 4, its configuration is 2 4, and half of the second shell maximum capacity of 8 electrons. And there are a number of similarities between hydrogen and organometallic compounds, since the group CH3, the group CH3 and hydrogen both have one remaining valency, and thus the position of hydrogen is not fixed, and hydrogen is best treated as a group on its own. Hydrogen is sometimes referred as the rock element. It is also called as rock element. And however, on the basis of its electronic configuration, that is 1s1, hydrogen is placed above lithium in the first group of Bohr's periodic table, but still this is not considered as the member of that group. Like this, we have placed the hydrogen at a separate position above it is not connected. It is above the first group elements. Okay, like this, we can see that in the periodic table if you look that. And so let's move to the next topic. That is the isotopes, allotropes, and molecular forms. So what are the isotopes of hydrogen, allotropes, and molecular forms of hydrogen? So isotopes. What are isotopes? We know that isotopes are those having the same atomic number but different mass number. So hydrogen also has his isotopes. There are 3 known isotopes of hydrogen, each possessing an atomic number 1 and atomic masses 1, 2, and 3 respectively. These are named as protium with symbol H1, and deuterium with the symbol H2. The above one, it is the mass number. Okay, and both of them have the same atomic number, or sometimes it is also denoted by capital D. And tritium, the third isotope is tritium, it is denoted by H3, and also is denoted by capital T. Okay, and the most common is the ordinary hydrogen, usually called protium, with atomic mass 1.008123, something like that, and it consists of one proton in the nucleus and one electron revolving around it. This isotope constitutes the 99.9% of the total hydrogen available in nature. The second isotope of hydrogen is called the heavy hydrogen or deuterium. It consists of one proton and one neutron in the nucleus and an electron revolving around it. Its atomic mass is 2.0142, and it constitutes only 0.016% of the total hydrogen occurring in nature. It is represented by the symbol D. Okay, D over H2. And the third isotope of hydrogen is called the tritium, and it consists of one proton and two neutron in the nucleus and an electron revolving around it. Its atomic mass is 3.0170, and it constitutes only 1 multiplied by 10 raised to minus 15. Look at the power percent of the total natural hydrogen. And this isotope is unstable, and it exhibits the radioactivity also. And now that was about the isotopes, and now we are going to talk about the talk about the talk about talk about allotropes. We are talking about the allotropes. So, orthohydrogen and parahydrogen. Similarly, ortho and para deuterium and ortho and para tritium. They are the allotropes of hydrogen. Orthohydrogen is denoted by orthohydrogen. Orthohydrogen is denoted by OH2. OH2, and that of the parahydrogen, that is pH2. pH2. Similarly, it is the ortho and para, that is deuterium and O and PD2, O or PD2, okay, or PD2, and that of the para, that is the tritium, it will be O or PT, PT2, PT2. They are diatomic, okay, and now the orthoisomers show parallel spins while para-isomers shows opposite spins or anti-parallel spins of protons. What do you mean by the spin? Ortho, I can draw that for the ortho. If these are the isotopes, then I'm drawing the para. So first I will show the ortho. Ortho, ortho, ortho have the parallel spin. Ortho high isomers have the parallel spin. Parallel spin. It is like this. They will spin in the same direction. That is parallel spin. Okay, and for that of the uh, that of the para isomers, they will be having the anti-parallel spin, anti-parallel spin, anti-parallel spin in the opposite direction. If he is rotating clockwise, the other one will be rotating in anti-clockwise direction. The two forms differ in their physical properties like its specific heat, thermal conductivity, boiling point, etc., but show similar chemical properties. But the forms are interconvertible. Paraform has lower energy, and at absolute zero, the gas contains 100% paraform or paraisomer. Due to the interconvertible nature, as the temperature rises, the paraform starts converting into orthoform. And at room temperature, these are in dynamic equilibrium with the equilibrium mixture containing 75% of the orthoform and 25% of the paraform. On decreasing the temperature, quantity of paraform increases in the solution. Okay, on decreasing, the paraform increases in the solution. Thus it is clear that the parahydrogen is favored at lower temperature. It's three times more presence at the room temperature, suggests that uh, orthohydrogen is more stable than parahydrogen at room temperature. And ortho and para interconversion is a slower process in the absence of catalyst. The suitable catalysts include activated charcoal, atomic hydrogen, metals. For example, we can say like iron, nickel, platinum, tungsten, and so on, along with paramagnetic substances like the oxygen and nitrogen monoxide, nitrogen dioxides, and cobalt 2 plus, and Cr2O3. So they're the we can use such catalyst for this process of interconversion between ortho and para isomers. And now we have to talk about the Next one, it is molecular forms of hydrogen. Molecular forms of hydrogen. What are the molecular form? Molecular forms of hydrogen, that is due to its high reactivity, protium or hydrogen combines with its own atoms or with the atoms of isotopes and exists in molecular forms as H12, it's, or H21, okay, or D2, or D2. Oh, sorry, here two will be here. Two will be here. It is diatomic. No, I am not showing the atomic number. Okay, H21 and or as the D, that is a D2, that is a deuterium. D2 is the deuterium, and this di-deuterium is called this one is called as the dihydrogen, and this one is called as the di-deuterium, and or H H23 that is called ditritium, along with HD, HT, DT, and such ones. Okay, they are also found as HD combined form in combined form of the isotopes HD, HT, DT, and so on. And I think we now need to look at some problems. So question is a very simple question. And what is the mass ratio of isotopes of hydrogen? So we know that the protium will be having the atomic mass 1, and the next isotope, that is deuterium, it is having the mass 2, and tritium 3. So the mass ratio will be 1 is to 2 is to 3. It was a very simple question, so option C is right answer. So let's move to the next topic, that is dihydrogen or hydrogen gas. We are going to learn more about the hydrogen or hydrogen gas. And being highly reactive, hydrogen always exists in its diatomic form, called the dihydrogen or simply the hydrogen. And we need to study the general methods of preparation of dihydrogen. Analysis of the previous year's examination papers reveals that the preparation of hydrogen is an important topic of this chapter, and generally questions from this topic can be seen in JE main or AIEEE examinations. The level of the question is moderate, and let's study the preparation or the um, methods of preparation of hydrogen. General methods of preparation of dihydrogen. Preparation of dihydrogen. Preparation methods. Okay, so first method we need to know, that is the laboratory method. How can you prepare hydrogen gas in the laboratory? Laboratory preparation. Laboratory method. And what is that? In laboratory, dihydrogen is produced by the reaction of zinc with dilute sulfuric acid. What is that? The reaction of zinc with the dilute sulfuric acid. Yeah, let's take zinc, and it reacts with the sulfuric acid or dilute sulfuric acid, and it gives the zinc sulfate along with the hydrogen gas. That is what we need. Okay, and actual changes that takes place here are the zinc will oxidize to zinc 2 plus, and H2SO4 splits into hydronium or H plus ion and HSO4 minus. HSO4 minus, HSO4 minus, and here 2H plus or H plus reacts with electrons, electrons giving that hydrogen or hydrogen gas. Okay, so here the reduction takes place, and by that reduction we get the hydrogen gas. Okay, this is a reaction or the changes that takes place actually in this reaction. Okay, so the next method is that the electrolysis of the water. By the electrolysis of water, electrolysis of water. How to prepare the hydrogen by method of electrolysis? Yes, in this, the electrolysis method, water is electrolyzed as like this. I'm going to show that here. Water must contain a small amount of acid or alkali, containing a small amount of acidic, that is acidic or alkaline, water must be acidic or alkaline, and that is electrolyzed, using some suitable electrodes, and we will get the products as H2, hydrogen at the cathode, and the oxygen gas at the anode. So this is the method, and we can separately show the reaction takes place at each the cathode and anode. At cathode the reaction takes place is that the hydrogen gas is liberated due to the discharge of H plus ions. Hydrogen gas is liberated due to the discharge of H plus ion, that is 2H plus 2H plus 2 electron. It's a reduction giving 2H, and that comes into hydrogen gas. Okay, and at the anode hydroxyl ions are discharged to give O2 gas, as shown here. I will show you. That is 2OH minus. The reaction takes place is 2OH minus gives H2O plus 2 electron, de-electronation takes place, and so plus oxygen, we will get a mono oxygen atom, and two of them combines to give the O2 gas. Okay, so that was the preparation method, and there are two cases of hydrolysis. We can, first case, suppose the hydrolysis is carried out in acidic media. I have told that with the taken water must be acidic or alkaline. In the first case is that the water is taken or the medium is acidic. For example, presence of H2SO4. Then at anode, the SO4 minus ions are not discharged, although they are present in larger quantity due to very high discharge potential of these ions as compared to that of the OH minus ions. And in the second case, similarly, if hydrolysis is carried out in the alkaline medium, for example, in the presence of KOH, that is potassium hydroxide, then at cathode, K plus ions are not discharged, although present in or the large quantity due to very high discharge potential of K plus ions as compared to that of the H plus ions. So that's the reason why we get in both the alkaline and the acidic medium we will get the hydrogen. And in the next method, and the next method is by the electrolysis of barium hydroxide. By the electrolysis of barium hydroxide. Barium hydroxide. That is, pure dihydrogen is prepared by the electrolysis of a warm concentrated solution of this barium hydroxide. That is BaOH twice. BaOH twice. In hard glass U2 with nickel electrodes. Here H2 is liberated at the cathode and O2 is liberated at the anode, and the H2 liberated or hydrogen liberated is passed over heated platinum gauze to remove oxygen as an impurity which is converted into water, and this H2 is removed by passing the gas over solid KOH uh, and P2O5. And P2O5. The H2 gas formed is finally reabsorbed over palladium foil, and from here it can be recovered whenever occurred by heating it to dull red heat. Okay, and for the above process, BaOS twice. For the above process, BaOS twice is preferred over NaOH, because if any CO2 is absorbed in the process and BaCO3 is produced, which being insoluble settles down at the bottom and does not interfere with the process, while Na2CO3 formed if you use NaOH is insoluble or is soluble in water and may interfere in the process, because the other one is insoluble, so it will not interfere in the reaction. And the next method is that the from active and moderately active metals, from active and moderately active elements or metals. Active metals, when react with water or any other protic solution, evolve hydrogen. Alkali metals are most active for this reaction. The reaction is violent in almost each case when we use any of the alkali metal for the purpose, and the least reactive is the lithium, and the reactivity increases as we move down the group. Large amount of heat is given in the reaction, and very often hydrogen evolved catches fire also. However, not all the metals give this reaction. Among S block elements, B does not react, that is, beryllium does not react with the hydrogen, does not react with the water, and that is, even if the water is hot or cold, beryllium does not react with the water, and to avoid the hydrogen. And the magnesium reacts only with the hot water. You know that magnesium reacts with only the hot water or the steam, while the rest of other members react with the cold water in non-violent manner. The zinc and the iron are even less reactive. They decompose water only when superheated steam is let over them high temperature at high temperature. Okay, and while so the reaction that occurs there is the in the case of iron, 3Fe plus 4H2O giving Fe2 Fe3O4 Fe3O4 plus hydrogen. This is a reaction taking when the superheated steam is led over the iron or it is same as that of the in the case of zinc. And most other elements are far less reactive to the displace hydrogen from water, and the process involves release of electrons by these metals, which is uh, taken up by H plus present in the solution, and the H plus is then converted in atomic hydrogen, and this atomic hydrogen combines with the other similar atom to form molecular hydrogen. And besides above written metals, that is like that of the magnesium or the iron or zinc, we can say that the elements like tin or aluminum also give similar type of reactions, but not with water. They give such type of reactions while we react with the dilute acid solutions. Certain metals zinc like the zinc, tin, and aluminum reacts with the alkali to evolve hydrogen also. And the reaction I can show reaction here. This aluminum reacts with NaOH, that is sodium hydroxide, that is an alkali, in the presence of or the alkaline water dilute, that is a dilute alkali, and reacts to give NaAlO2, NaAlO2 hydrogen and hydrogen. And also I can show the reaction of zinc. Zinc reacts with the alkali NaOH, sodium hydroxide, to give Na2 ZnO2 and hydrogen. And in the case of tin reacts with also the NaOH, dilute NaOH, that is plus H2O plus H2O, giving Na2 SnO3, and we will get the hydrogen as the byproduct. Okay, the next method is the ionic from the ionic hydrates. From the ionic hydrates. Ionic hydrates. Ionic hydrates. The ionic hydrates of alkali and alkaline earth metals also evolve such H2 on reaction with water. That is, if I take calcium as an example, or the hydrate of the calcium, that is CaH2 plus 2H2O, it reacts with water to give calcium hydroxide. Calcium hydroxide, and what we need, that is the hydrogen. That's the byproduct. So this is the reaction. It's the reaction of ionic hydrates with water and gives the hydroxide, and also we will get the hydrogen gas as the result. And these were the simple methods, and now we need to study the commercial or industrial methods of preparation of dihydrogen, which are there. Some of them are also important, like the Bosch process and Lane process, Nelson or Cashner-Kellner process, and so many like that. Let's look at that also. So the first method is We are talking about the industrial preparation. Okay, the industrial preparation. Industry writing does not seems to be smooth because I am using a mouse and it is difficult to write with this mouse. Okay, and industrial methods, and the first one it is the electrolysis itself, electrolysis of the water, electrolysis of water. That is, in the electrolysis process, dihydrogen is produced by the that is a electrolysis of water containing 15 to 20 percentage of H2SO for the sulfuric acid. And here also hydrogen is liberated at cathode while O2 is liberated at the anode. Oxygen is liberated at the anode, as the same as that we discussed before. And the second method is this important one, that is the Bosch process. Bosch process. In the Bosch process, the dihydrogen is prepared from the reaction of water vapor by the carbon. As the reaction I can show here, coke reacts with this coke. Okay, carbon, we use the coke in the form of coke, and the coke reacts with the superheated steam. Superheated steam, that is of water, gives the syngas or water gas, that is the combination of carbon monoxide and hydrogen, that is called the syngas or synthesis gas or water gas or water gas or water gas. And further reacts with the steam in the presence of catalyst, and usually a mixture of iron, chromium and cobalt reacts with the steam again in the presence of the catalyst like the iron, chromium or the cobalt, and gives the carbon dioxide, which is a independent gas, and gives the hydrogen as a result. Okay, and the CO2 is removed either by washing under pressure of the 25 to 30 atmosphere, or by reacting with the KOH, so it is a alkali. And that was the reaction. What was that? We took the coke and reacted with the super heated steam, and it gave the combination or the syngas or water gas, that is the combination of the carbon monoxide and hydrogen, and it further reacts with the steam again in the presence of the catalyst like the iron or something like that, that is a chromium, cobalt, and gives the product, that is carbon dioxide and hydrogen. And carbon dioxide is removed by the washing under the pressure from 25 to 30 atmosphere, or by reacting with the potassium hydroxide. That was the reaction here in the Bosch process. Okay, simple. And the next process, it is the Lane process. Lane process. Lane process. In the Lane process, dihydrogen is produced as by the reaction of the iron with superheated steam. That is, you can write it as 3Fe. This iron is heated to almost 900 degrees Celsius, and it is reacted with the superheated steam, and gives Fe2O3 and H2O, and hydrogen. Okay, Fe3O4, Fe3O4, and hydrogen, and this Fe3O4 can be reduced by passing it over the carbon monoxide, and it is reduces it to iron, Fe. So that was the reaction or the Lane process, by the reaction of the iron with superheated steam, and by further reduction with carbon monoxide gives the hydrogen as a byproduct. And the next method is Nelson or Kastner-Kellner process. Nelson process or Kastner-Kellner process. Nelson or Kastner-Kellner process. H2 or the hydrogen is produced in Nelson or Kastner-Kellner cell by electrolysis of brine solution. This brine solution is the aqueous NaCl by the reaction of the brine solution in them. That is, the hydrogen is can be produced by the reaction of or the Kastner-Kellner cell by the electrolysis of brine solution. By the electrolysis of brine solution, that is the reaction of Nelson process. And the next one is from the production from the petrochemicals. From petrochemicals also we can form hydrogen, and presently near about 77% of the industrial hydrogen is produced from the petrochemicals. For example, 18% from the coal, and 4% from electrolysis of brine solution, and 1% from other sources also. And the caution point here is that hydrogen and carbon dioxide can be easily separated from each other by bubbling the gaseous mixture through water, in which carbon dioxide is fairly soluble and hydrogen is virtually insoluble. It is a reaction of H2O plus CO2 and giving H2CO3. Okay, and now we need to go for some problems. The first problem, in the method of bulk preparation of hydrogen by electrolytic method, the role of electrolysis is which one of them? That is the question. So first option is decrease the boiling point of water. Electrolyte is not decreasing the boiling point of water, nor increase the boiling point, and increase the ionization of water. It is also not correct. But the last one, that is the electrolysis of acidified water using platinum electrodes gives a hydrogen. That we know that. So that's the correct option. Increases the charge carrying particles in water. And the reaction there was the 2H2O, 2H2O giving by the electrolysis of water. Okay, electrolysis in the traces of acid or base, acid or base, we get the hydrogen gas, TH2 gas, and oxygen. The role of electrolyte is to make the water conducting by increasing the number of charge carrying particles, that is the ions. Okay, the role of the electrolyte we use acid or base is to increase the charge carrying capacity in order to make it more conducting for the process to happen. That is the formation of the hydrogen and oxygen. And the next question is, which of the following reaction increases the production of dihydrogen from synthesis gas? So here the production of synthesis gas, that is the process of producing syngas or synthesis gas from coal, is called the coal gasification. Coal gasification. Sorry, coal gasification. And the reaction is carbon reacts with, or the coal reacts with the steam, giving carbon monoxide and hydrogen, that is the syngas in the presence of nickel or something like the chromium or something like that, in the presence of nickel and at the temperature 1270 Kelvin. 1270 Kelvin. The production of hydrogen can be increased by reacting carbon monoxide of the syngas with the steam in the presence of iron chromate as catalyst at 673 Kelvin. Okay, at 673 Kelvin, the production can of the hydrogen can be increased by reacting carbon monoxide of the syngas with steam in the presence of iron chromate as catalyst at 673 Kelvin, and that reaction is here CO plus H2O, CO plus H2O, giving CO2, giving CO2 plus H2. So here the catalyst we use like the FeCrO4, FeCrO4 at C7673 Kelvin. So if we were asked to find the reaction of production of syngas, so the equation will be or the answer will be A. But here, which of the following reaction increases the production of dihydrogen from synthesis gas? So this is not the reaction. So the reaction will be the second one. Carbon monoxide react with the water to give carbon monoxide and hydrogen. So option C is the right answer. Option C. And let's go, or let's move to the next topic. That is the physical and chemical properties. Uh, physical and chemical properties of dihydrogen. Of dihydrogen. What are they? First, we must talk about the physical properties. That is a physical properties. Which are the physical properties? Hydrogen is a colorless, odorless, tasteless, diatomic gas, and it is the lightest element known. And being non-polar, hydrogen molecules have a very weak intermolecular forces, due to which its melting point and boiling point are very low. Its critical temperature is minus 273, minus 2386.9 degree, and can be liquefied at the temperature of minus 252.8 degree and solidifies at minus 259.8 degree. Metals like nickel, platinum, palladium, iron, gold, and so on can absorb or occlude large volumes of hydrogen gas at different temperatures, and palladium can occlude 1,000 times of its own volume of the hydrogen, and that's why you use palladium for the storage of hydrogen gas. And the bonding forces within hydrogen molecule are exceptionally strong, and hence it is thermally stable. And so we need to talk about the reaction of the hydrogen with non-metals. Reaction with non-metals. On combination with non-metals like oxygen, nitrogen, or fluorine, or chlorine, or bromine, and so on, it forms covalent compounds like H2O, and NH3, NH3 in the case of fluorine, or any halogens forms the halides like HX in the general form HX. I can write it as HX. X denotes the halogen, and so on at higher temperatures. Okay, and however, it remains unreactive with above written elements at ordinary room temperature. And because at ordinary temperatures, hydrogen exists in molecular state in which atoms have stable helium structure. To be converted into atomic hydrogen, either high temperature, that is from 700 to 800 degrees Celsius, or a catalyst like nickel, platinum, or palladium, such things, which bring down the temperature to about 250. We can convert a 250 degree, about 250 degree, if we have catalyst like nickel, palladium, and something like that. And okay, then is required such catalyst is required, after which hydrogen molecules dissociate into atoms, and these atoms then combine with non-metals to form the required element or required product. Okay, and now we need to talk about the reaction with metals. On combination with the metals like lithium, sodium, potassium, cesium, calcium, etc., the electrovalent hydrates are formed, and these are good reducing agents and are in fact good sources of hydrogen. The hydrates are formed can conduct electricity in fused or molten state and possess high melting point. And the next property we need to talk about the reducing agents, or the reducing property. Okay, reducing property of hydrogen. Reducing property. Hydrogen has the property to reduce the oxides of less electropositive elements. For example, CuO plus hydrogen, it is copper oxide plus hydrogen, reacts with hydrogen to give copper. It reduces copper oxide to hydrogen, and to copper and H2O and water. Okay, and similarly, uh, with Fe3O4 to give the elemental uh, iron and H2O. So this was also Fe3O4 is also reduced to iron and forming water. And certain chlorides also get reduced as like silver chloride, that's 2AgCl, reacts with hydrogen to give the metallic silver, and HCl is formed as the byproduct. And however, hydrogen does not have the ability to reduce the oxides of alkali metals and alkaline earth metals. Okay, and now we need to talk about some uses of the hydrogen also. Which are the uses of hydrogen? Uses of hydrogen. Sorry, uses. Uh, Uses of hydrogen. Uses of hydrogen. What are they? The first is the manufacture of ammonium by Haber process, and second, manufacture of hydrocarbons and their derivatives, manufacture of hydrochloric acid or metal hydrates, like that, and the reduction of heavy metal oxides to form to the metals, heavy metal oxides to the metals in metallurgical process, and in oxyhydrogen and oxyatomic hydrogen torches for cutting and welding. And besides, dihydrogen is also used as rocket fuel in bubble chambers as liquid hydrogen for the study of high energy particles and in fuel cells. Remember that dihydrogen is considered as very good fuel as it does not cause any pollution and produces greater energy per unit mass of fuel as compared to the gasoline or other fuels. So let's see the other topics in the next part. Okay, and to know more about the cloud vendor, visit our website. You can Google by typing cloud vendor Gaurish. Site appears as the first result, and or simply search cloud vendor and you will get the site as the third result. And also you can follow us on different social media platforms, and you can follow us on Instagram, and you can follow on WhatsApp. I have created a WhatsApp group for discussions on different doubts you have, and the links are given in the description box. Also a Telegram group for discussion and the same purpose, and a channel is also formed for giving off your learning steps, and all the links are given in the description box. You can check it later. You can also ask your doubts as comments in YouTube, and if you want more videos which would be uploaded in the coming days, please subscribe our channel and press that bell icon for getting notifications on time.
Hope you guys understood the topic. Thanks for watching my video. Always be free to ask questions. Subscribe to my channel for more videos. If you like this video, share it with your friends. See you guys.